Particle entanglement. Achieving particle entanglement is a delicate process that involves creating correlation between two or more quantum particles, such that their quantum state are interconnected, regardless of the distance between them. This is typically done using certain technique that manipulate particles' properties such as spin, polarization, or momentum in controlled experiment. Spontaneous parametric down conversion (SPDC). SPDC is one of the most common methods used to entangle photons. In this process, a single high-energy photon, often from a laser, passes through a nonlinear crystal, such as beta barium borate (BBO). When the photon interacts with the crystal, it can spontaneously decay into two low-energy photons, which are entangled. The resulting photon pair is often in a polarization entangled state, where the polarization state of the two photons are correlated. For example, if one photon is measured to be vertically polarized, the other will be horizontally polarized, or vice versa, even if they are far apart. Polarization in physics refers to the orientation of the oscillations of waves, especially in the context of electromagnetic waves like light. Unpolarized oscillates in many directions. Polarized oscillates in a specific direction. Steps for SPDC. First, a laser beam is directed into nonlinear optical crystal. Second, the photon from the laser is then converted into two low-energy entangled photons. Third, the two photons are now entangled in terms of properties like polarization, momentum, or energy. Atomic cascade in spontaneous emission. In this method, an existing atom, or ion, is made to decay by emitting two photons in a particular entangled state. This is achieved by having the atoms first absorb energy and then emit two photons as it returns to the lower energy state. The two emitted photons can be entangled in terms of polarization or momentum. The decay process can be controlled so that the properties of two emitted photons are linked. Quantum dots are tiny semiconductor particles that can be used to produce entangled photon pairs. When excited, quantum dot can emit photons that are entangled. The quantum dots are specifically engineered to emit photons that exhibit specific entanglement properties, such as polarization entanglement. Entanglement by interaction in a single photon source. In certain experiment setups, entanglement can be achieved by sending two photons through a beam splitter or other nonlinear optical components, causing interactions that lead to entanglement. A well-known example is used parameter down conversion with the cavity or using interferometers to induce interactions that correlate the state of the emitted photons. Controlled collisions of atoms or ions. In experiments with trapped ions or ultra-cold atoms, entanglement can be achieved by making two atoms or ions interact in a controlled way. For example, the two ions in a trap can be entangled using laser pulses that induce interaction between their electronic states. This method often requires precise control of electromagnetic fields and laser systems. Techniques such as quantum gates in trapped ion systems are used to entangle qubits, quantum bits. Ion is an atom or molecule that has gained or lost one or more electrons. resulting in a net electrical charge, positive charge if lost ion, negative charge if gained electron. Entanglement through measurement. Measurement device independent entanglement. This technique relies on the idea of entanglement swapping, where entanglement is transferred or swapped between particles using intermediate entangled pairs and subsequent measurements. For example, the two unentangled particles can be entangled by first creating a third particle that is entangled with each of the original particles. Through a process of measurement or the intermediate particle, the two original unentangled particles become entangled. Superconducting qubits. In quantum computing, superconducting qubits, other words artificial atoms, are widely used to generate entangled states. These qubits can interact with each other in a way that induce entanglement, particularly using quantum gates. Superconducting circuits allows for manipulation and entanglement of qubits, which are used to perform quantum computations. Bose-Einstein condensate. At extreme low temperatures, atoms can form Bose-Einstein condensate, where many atoms enter the same quantum state and exhibit collective entanglement. BECs offer a unique platform for creating microscopic quantum entanglement, and scientists have successfully created entanglement in such systems. Key steps in achieving entanglement. Prepare a suitable system. You need particles that are capable of interacting with each other and forming entangled states. This could be photons, atoms, ions, or superconducting qubits. Induce interaction or decay. Use methods such as parametric down conversion, atomic emission, or laser interactions to induce the creation of entangled pairs. These methods typically exploit quantum mechanical processes that link the particle states. Verify entanglement. After creating entangled particles, it is crucial to verify that they are indeed entangled. This is often done through Bell's theorem experiments, which test whether the correlation between the particle states are stronger than what can be explained by classical physics. Techniques such as Bell type inequality tests or quantum state tomography are used for verification. Loss and decoherence. Achieving and maintaining entanglement can be difficult due to environmental interference and decoherence. This is particularly challenging for systems with long-range entanglement. Measuring entanglement in some systems require extremely precise and delicate equipment, as quantum systems are sensitive to disturbance. Thank you for listening to this podcast on particle entanglement. Until next time, curiosity adventures through the fields of science.